Okay, so another problem here is number 16. They ask us to find all relative extrema of the function, and they say use the second derivative test when applicable. Okay, so here's a function they give us, and the first step is they want us to find any relative maximums or minimums, and as we know now, those can only occur at critical numbers. So the first question is, if there is going to be a relative maximum or a minimum, what are the critical numbers? Okay. So for that, we go to the first derivative. Remember, critical numbers have to deal with the first derivative being 0 or undefined. Sometimes we'll figure out when the second derivative is 0 or undefined, but when they say critical numbers, they're talking about the first derivative. So, okay, what are the critical numbers of this function? Well, we get the derivative, and we get, in this case, we back up here, this is 2x squared plus 6 to the power 1/2, right? So we're going to use the generalized power rule here. Okay, so 1/2 times 2x squared plus 6 to the power negative 1/2, right? You bring the power down and decrease it by 1, okay? And then you have to multiply by the derivative of what's inside, and that's 4x. Derivative of 2x squared plus 6 is just 4x. Okay, so the first derivative for this function is going to be 2x over the square root of 2x squared plus 6. Okay, so what are the critical numbers of this function? Okay. Well, actually, remember, if we need to figure out where the function, where the derivative is 0 or undefined. Can the derivative ever be 0? So what about this? Is the derivative that we just found ever equal to 0? Well, yeah, it can be 0 whenever the numerator of this fraction is 0. Of course, that's going to happen when x is 0. Okay. So we've got one critical number, okay, so far. Now, what about the denominator? Okay, well, we can have also a critical number whenever a function's undefined. So we could have a critical number whenever the denominator is 0. Okay. So is the derivative here ever undefined? That's the next question. Well, that's only going to happen if, well, one of two things. Either the square root doesn't make sense because this is negative, or if this is ever equal to 0. Okay. So what about this? Is 2x squared plus 6 ever equal to 0? Okay. Well, actually it's not going to be, because we get 2x squared equals negative 6, or x squared equals negative 3. And of course we can't take the square root of this equation. So the denominator here is never 0. Okay, that's good. That means we only have the one critical number. And in fact, this is never negative either. If you look at the expression inside the square root, 2 times any number squared has to be at least 0. And if we add 6 to it, it's still going to be positive. So definitely this is never negative. The square root always makes sense. And by the way, the function has a domain of all real numbers, because we can't make this expression inside negative. But it's also never 0. So we just have the one critical number, okay, 0. Okay, so one critical number, that means that when x is 0, okay, and y is, f of 0, whatever that turns out to be, we could have a maximum, we could have a minimum, or we could have neither. Okay. Now, the question is, what happens at this point? Okay, when x is 0, do we have a maximum? Do we have a minimum? Do we have neither of the above? Well, that's where we need the second derivative. Okay, the second derivative test says that if you have a critical number, okay, where the derivative was 0, which we have here, okay, if the second derivative is positive, that critical number gives you a minimum. If the second derivative is negative at this number, it'll give you a maximum. Okay, so what's the second derivative of this function? Okay, well, it's a little tricky because, again, it's the quotient rule, but we can go ahead and use it. Quotient rule says take the denominator times the derivative of the numerator. Okay, derivative of the numerator is 2. Okay, minus the numerator times the derivative of the denominator. I have to erase this and get some more room, but remember, we just have one critical number so far. Just x equals 0. That's what I need to keep here. Okay. So the numerator times the derivative of the denominator. Okay, well, actually, we already computed the derivative of the square root of 2x squared plus 6, right? That's what our first derivative was. So actually, this whole thing is the derivative of the denominator, 2x over square root of 2x squared plus 6. Okay, you see what I did there? This should be the derivative of the square root of 2x plus 6. But look at what we found. This derivative of the square root of 2x squared plus 6 is this. So I just plugged it in. Okay, I'm kind of using something I've already done. Again, it's recycling. Okay, and this is all over the denominator squared. Well, that's the denominator here squared, and when I square that, it's just 2x squared plus 6. Okay. Now, normally we would like to simplify this mathematically, but really all we have to do to use the second derivative test is to figure out if f double prime of 0 is positive or negative, right? Because if we know that the second derivative is positive at a critical number, it means that the critical number is a minimum. If the second derivative is negative at this value, it's a maximum. Okay. Well, actually, you can do this without too much work. If you put 0 in for x here, quite a bit of this stuff's going to drop out. Okay, if I put 0 in for x, I'll just get the square root of 6, okay, times 2, so 2 square root of 6, okay, minus, well, if I put 0 in for x here, there's some zeros in the numerator, so that whole expression is going to turn out to be 0, right? You know, for instance, negative 2 times 0 times anything else is 0, so that's all 0. And if I put 0 in here, in the denominator for x, I'll get just 6, okay? So, you know, it's 2 square root of 6 over 6, but more importantly, the second derivative is positive, okay? So that means when x is 0, we will have a relative minimum. That's the second derivative test. Okay, so I can actually erase the derivative. We got what we needed out of it. The second derivative is positive at our critical number. So we're going to have a relative minimum at the point 0, comma, f of 0, right? Whatever the y-coordinate is when x is 0 in our original function. Well, it's going to be the square root of 6. Right? If I put 0 in for x, I'll just get the square root of 6. So if you were to graph this function, it might look kind of complicated. It will have a relative minimum, though, at this point. No other relative minimums or any relative maximums. Okay.